Hello, geometry class, and welcome to today's notes on section 10.2 congruent chords. So what I'm going to be doing in this video is going over the theorems from section 10.2, kind of explaining where they're coming from and looking from some examples. And I'm going to bet as I begin to make more and more of these videos, that's pretty much how they're all going to work. So please take notes as I go. I would encourage you to draw the diagrams that I have, maybe even have the textbook out in front of you as I'm going so you can follow along. And of course, take note of any questions that you want to ask me when we get to do our class session tomorrow. Okay, so remember, a chord is any segment that goes from one endpoint on a circle to another endpoint on the circle. A diameter is a chord, of course. It's the longest chord that you can draw in a circle. So theorem 77 says that if two chords of a circle are equidistant from the center, then they are congruent. And equidistant means, of course, that they are the same distance away from the center. So in this diagram, we are given circle P. We are given px and py are perpendicular to their respective chords and that they're congruent. And we need the fact that they are perpendicular because that's how we measure distance. If we are not given that these are perpendicular, we can't really conclude anything else. All right. So how would we show that AB and CD are in fact congruent to each other? Well, if you recall, one of the theorems that we saw in the previous section, if I go from the center to a chord and I make a right angle, I end up splitting the chord into two equal parts. I bisect that chord. So I could say that AX and BX are congruent to each other. And then over here, I could say that CY and DY are congruent to each other because PY is also a bisector. All right, so remember, the hint of all hints for this section is when in doubt, draw any radius, and I'm going to draw any radius from A to P and from D to P. And since all radii in a circle are congruent, we know that the two blue segments, PA and PD, are congruent to each other. We were given PX and PY are congruent, and since we have right angles there, we can use the hypotenuse leg theorem to say that triangle PAX and PDY are congruent to each other. So by CPCTC, AX and dy must also be congruent. So let me throw in a second tick mark here to show those two are congruent. And we have two segments where the halves are congruent. So that means that the wholes are going to be congruent. And that's where we get AB and CD congruent to each other. Okay, so again, just to summarize, we draw on the radii. That's your hint. We get the two triangles by hypotenuse leg, these segments by CPCTC, and if the halves are congruent, the wholes are congruent. So if I know that two chords are the same distance away from the center, they have to be congruent to each other. That's theorem 77. Theorem 78 is basically the converse, which means that what we have here is a biconditional statement. But theorem 78 says that if two chords are congruent, then they are equidistant from the center. So if I put the two together, I could say in a circle, two chords are congruent if and only if they are equidistant from the center. All right, so in this diagram, we are told that A, B, and CD are congruent. So I have the congruent chords. OE is perpendicular to AB, and OF is perpendicular to CD. Now, maybe in a future problem, you might just be given the congruent chords without OF and OE drawn in. But draw those in if you need to, and you're basically just drawing in perpendicular lines there. And what we are going to try to show is that OF and OE are congruent to each other. Okay, so since the wholes are congruent, I can say the halves are congruent, and I know that F is a midpoint and E is a midpoint because of the theorem from section 10.1 that says if I draw a line segment from the center to a chord at a right angle, then I find the midpoint. I split the chord in two. So I know that DF is, or F is a midpoint and E is a midpoint. And again, I can say that if the wholes are congruent, the halves are congruent. So I have DF and EB congruent to each other. What's missing? Gosh, if only there was something I could do when I have a diagram like a circle. And oh, that's right. I'm going to draw in a radius because that's what we do in this section. When we don't know what else to do, we're going to draw in a radius. And I'm going to draw in DO. I'm going to draw in BO. And again, I know that DO and BO are congruent to each other because all radii in a circle are congruent. And now I have two right triangles, DFO and BEO, and they are congruent by the hypotenuse leg theorem. So that means that OF, let's see if I can get 3 tick marks in there. Oh, that's a little awkward. Okay, and 3 tick marks here. 1, 2, 3, close enough. Yeah, so they're going to be congruent by CPCTC. And since OF and OE are congruent, yeah, we know now that the chords are equidistant from the center. Okay, so that's theorem 77 and theorem 78. Let's start applying these two theorems to some practice problems. Okay, so here we have circle O, I have AB and DC congruent to each other, and we want to find the length of OP. So we're told that OP is 12x minus 5 and OQ is 4x plus 19. All right. Well, if we want to solve for x, we need an equation. And what equation can I use with 12x minus 5 and 4x plus 19? One of the things you might guess is like, well, just set them equal to each other. And of course, we want to know why would they be equal to each other? Well, if A, B, and C, D are congruent chords, they are equidistant from the center. So I can say, yep, OP and OQ are the same length. So 12x minus 5 is equal to 4x plus 19. So now I'll begin solving for x. X is on one side, numbers on the other. So 8x is 24. And of course, that means that x is equal to 3. So if I know x is 3, let's plug in 3 for x up here. So OP is 12 times 3 minus 5, which is 31. So the length of OP is 31. Okay, that's a pretty simple example, but it's a perfect application of our theorem. Okay, next example. Here we're told P is the center of the circle, and it's also the midpoint of MN. I have perpendicular up here, perpendicular down there. PM is perpendicular to AB, and PN is perpendicular to BC. We want to show that ABCD is a parallelogram. And actually, if you really think about it, ABCD isn't just a parallelogram. It will end up being a rectangle, but that's not what we're asked to show here. We're just asked to show that it's a parallelogram. So how can we do that? Well, I know it's a while ago, but there were 6 ways of showing that a quadrilateral is a parallelogram. And the way we're going to use here is I'm going to have one pair of sides that is both congruent and parallel. My congruent sides and parallel sides are going to be AD and BC. So if I can show AD and BC are both congruent and parallel, then I'll know that it is a rectangle. Well, just by looking at the diagram, I see a right angle here and a right angle there. I think it's pretty clear I can say that AD and BC are parallel to each other because I have one line segment that's perpendicular to both lines. So AD and BC are going to be parallel to each other. Okay, that's first. Second, since P is the midpoint of MN, I can say PM and PN are congruent to each other. That's the definition of a midpoint. And since PM and PN are congruent to each other, that means that the two chords are in fact equidistant from the center. And if the two chords are equidistant from the center, well, we just saw a theorem that says they're going to be congruent. So AD and BC are not only parallel, but congruent. And that is the way I said we were going to show that ABCD is a parallelogram. All right, on to our last example. Here I have a rectangle, which is 16 by 12, and it is inscribed in the circle. Find the radius of the circle. All right, so how can we do this? Well, let me get a nice color here. Let's go purple. All right. This is 16. This segment down here is also 16. So, of course, these two things are going to be the same because they're equidistant from the center. And what that means is that each one of these segments has to be 6. All right. Okay. And then I can also do the same thing because um, the 12 chords are equidistant from each other. And let me get another line segment going here. Let's do a different color. Let's do orange. Okay. So that means that if I make a right angle there and a right angle there, those are also going to be equidistant. And I can say, well, if the whole thing is 16, then each piece of this is 8. Now, maybe you can imagine where this is going. Let's see. Well, they want the length of a radius, so guess what we have to do? Draw in a radius like that one right there. And what I have is a 6, 8. Wait for it. No, you don't have to wait for it. You're watching a video. It's 10. The radius is 10. So that is the radius of the circle. The radius is 10. 3, 4, 5 triangles always coming back to, I don't know, haunt us. They're friendly. They shouldn't haunt us. Rear its ugly head. No, they're actually fairly nice to look at. So, but here they are again, helping us out. The 3, 4, 5 triangle. Okay, so you have some textbook questions to do tonight, and you can take a look at those. We'll go over them in class tomorrow. Have fun, everybody.